But yes, it is one of those things that often only maybe the top two sets will do. They'd do multiplying out brackets probably with everyone, because that's easier, isn't it? It's kind of more straightforward. But going back the other way is trickier. So yes, the only additional thing that the AS Maths has is this little bit where you could have things that are like quadratics, and this bit about the discriminant, which we'll talk about a bit later. But otherwise, the quadratics that they're expected to do at GCSE is pretty much the same as AS. So yes, why do we factorise? So factorising is when we basically find the factors of the quadratic, which entails putting them back into two brackets. Why do we do that?
From y to find the values of 0, isn't it?
Yeah. So
when x is
yeah.
When y is 0, isn't it?
Yeah. So when y is 0, that's the solution to the equation, basically, when it equals 0. And then that helps us to sketch a graph, because where y is 0, that's the x-intercept. So it kind of gives us an algebraic reason and a graphical reason. So think about two numbers that multiply to give 0. Can you give me two numbers that multiply to give 0?
Anything with a 0 and anything else, really.
Exactly. So that's the point, basically. Hopefully, as it says, one of your pair of numbers is 0, because otherwise, well, it would be impossible. So anything multiplied by 0 is 0, and it's that fact that we use to solve the equations. So if we've got two things multiplied together and they equal 0, then one of them must be 0. So if that's the case, when we've got, for example, x minus 2, x plus 5 equals 0, we know that either x minus 2 is 0 or x plus 5 equals 0. So we consider each of those possibilities, and then we have basically a little equation. In order to get 0, x must be 2. 2 minus 2 is 0. Or we can just think of solving x minus 2 equals 0 and taking the 2 to the other side. And the same on this side. In order to solve x plus 5 equals 0, x must be minus 5. So those are our two possible values for x. So this is the kind of funny way that we write it as well, and I think the kids find that a bit weird, because they're like, well, why does it have to be either or? Can't I write and? And it's one of those bizarre things that, because really it should be one or the other, it's an or, but it doesn't matter at all what they write in the exam, as long as they show two solutions, basically. Often they just write x equals 2, comma, minus 5, and that's acceptable too. But generally we write or. And the key thing about this, which is often something that they forget, is that in order to factorise it, it must be equal to 0. If there's still a number over here, you need to multiply everything out, collect that number over the other side, and then refactorise it, which was a mistake I made in my first lesson teaching quadratics, when I could not figure out why on earth I was not getting the right answer. It's because I'd left a number here. So I'd factorised it like this, and I was sort of saying x minus 2 equals 3, so x equals 5. That's not right, because it's not true that this is not the case in lesson 0. Now, three ways that you could factorise a quadratic. It may be that it's just a case of taking out a common factor. It may be that there's the difference of two squares, which we'll look at in a second. Or the more typical one is a trinomial. That's the typical ax squared plus bx plus c, and you're looking to get two brackets out of it. And this is sort of saying how you do it. You know, you list the pairs of factors and look at them. But I'm going to do that a bit more as well. So have a look at these. I want you to factorize them. So put your hand up when you've done that.
Okay, just so you know, I'm struggling with the last one. I'll carry on.
It may be that I'm just being a bit mean here, which I am.
Yeah, I'm thinking of the quadratic equation to get this one done.
I know. Yes, exactly. So when I say factorising, I'm actually here just talking about taking out the common factor. So yes, because that last one, yeah. So when we're talking about factorising here, the key thing is that because they get so used to seeing this trinomial and then trying to put it into two brackets, they forget about just the fact that factorising means taking out a common factor. And they forget how to do ones like these. So the reason I've popped this in is just that always make sure that they are remembering the basics, such as just taking out the common factor, but then aren't necessarily two brackets. So here, 3x is in common with both, so that's what we take out. Here, yes, you can't actually factorise this. You can only take out the common factor of 2. So it was a deliberate...
That was cheeky.
But yeah, I was being deliberate.
Sneaky.
I know, and it's the sort of thing though that's quite nice to put up before they know the formula, but when you've done factorising, when they're sat there going, what, I can't do this, and it can actually lead quite nicely into the formula, which is in fact where I had the slide before, and then I moved it up here to be earlier, because I thought, no, it's too basic to have later, but now I never remember why I put it later. I think I'll switch it back. Yes, so this highlights to them that just because you see a trinomial doesn't mean you can factorise it into two brackets. So yes, really this should go before we get onto the formula. But there are still options to take out other factors, which they do forget. And you'll see them doing all sorts of things. What's hilarious, you'll often see them do things like two brackets with x plus 0 and x plus 5 in order to kind of create their two brackets. So, you know, another one which they just kind of have to be able to spot is the difference of two squares. Have you come across this before?
Yes. One's just a plus and the other one's almost like a mirror image, a minus.
Yeah. Wayne, have you come across this before?
Yeah, but no, I can see it's 9 minus y and then brackets 9 plus y, yeah, I guess.
Yeah, exactly. Yeah. So they've just got to be able to spot that if we've got a square number and a minus in between, so they're both, if they're both squares, then they can, you know, recognise hopefully that it's the difference of two squares. So yeah, that's 9 plus y, 9 minus y. What will the next one be, Robert?
That's be 2x plus 3, 2x minus 3.
Yep, good. Now, I'll put a pink and big capital first next to it as well. Why have I put that?
Guessing because the x squared value is bigger.
No, I think I put think because those aren't square numbers at the moment, but how can you make them square numbers?
Mm.
Right, so you could take something outside to start with, maybe.
Yeah.
Take the 3 out.
Yeah.
And then do 2 mirror images of, what would it be, 4x minus 1? 4x plus 1?
It would be 1, there'll be a 4 there, so the square root of it would be 2. So 1 minus 2x, 1 plus 2x. So yeah. Yeah, exactly. So, I mean, that is really difficult to spot, that one. I think that would be quite mean if they were given that. Because there's 2 steps in it. You've got to take out a common factor first, and then see that that is then the difference of 2 squares to get to that bit. And the last one, it's a bit of a weird one.
That was the 3x and the 4y.
Yeah, exactly. And plus 1 minus. Obviously, that wouldn't be a quadratic. That's just a case of how to factorise that. Good. So you sort of kind of need the kids thinking about common factors and difference of 2 squares. Oh, what about x squared plus 4?
It's not going to be a difference of squares because you've got that plus sign in the middle.
Yeah.
You're not going to be able to factorise that down.
No, and later when we talk about graphically what's happening, the graph of this, in fact, if I were to draw it.
And that one doesn't even sit on the x-axis, does it? It sits
Exactly.
above.
It's going to be up here. And so there are no solutions. So there's nothing, you know that there will be no factorising. And I think the interplay between graphs and algebra can help to make that really straightforward, can't it? To me, that's really obvious because I look at that and I know that that isn't going to cross the x-axis, and so there are no solutions when that equals 0, so I'm not going to be able to factorise it. But the students really find that very separate, so it's good sort of from the off to start bringing the two together, which I will be doing it in a minute. So I've uploaded some resources. There's a sort of one where you can use Autograph or some sort of graphing package where they start from graphing and move towards the algebra. Or there's one that has kind of little bubble steps to help them factorise step by step. Or there's the next 2 slides which I have, which are step-by-step factorising of a trinomial like this. So a trinomial just has 3 terms. Binomial has 2 terms. So to factorise this, the traditional way that we say is to basically think about 2 numbers that add together to get the 4 and 2 numbers that multiply together to get the minus 12. And they're kind of expected to use trial and error to think, okay, what 2 numbers? They generally start with this one, don't they? They're multiplying and work their way down, going things that multiply to give 12, 3 and 4, that's not going to give me 4. 12 and 1, that's not going to give me 4. Oh, 6 and 2, that'll be right. Okay, and I need one of those to be negative. So I want a positive 4, so it's going to be 6 and minus 2. So that's the thought process that I go through very quickly in my head. The students find it really tricky. So there's a number of things that they do. A lot of them like to write out all the different possibilities. They get quite wound up about the sign, and they sort of say to me, oh, because it's a minus, there'll be different signs. Well, yes, that will happen quite obviously as you try to do it. But yeah, so they end up writing minus 6 times 2, minus 2 times 6, you know, all the different possibilities. They write them all out, and then they see which of those add together to get 4. So it can be quite this is quite a time-consuming thing for them. So then they put those two into the brackets. Those are their factors. X plus 2 and x minus 2 are the factors. And it's quite useful that you start right away with this terminology because they'll be needing it more and more as they get towards AS level. So those are the factors. When we want to solve the equation, all of that is equal to 0. And therefore, we can then look at that either x plus 6 equals 0 or x minus 2 equals 0. And we solve these little things to show that in order for this to work, that must be minus 6 and that must be 2. And then once we've got to this point, the x values are the roots. Sorry guys, can you mute your speakers at the mic? So those are the roots of the equation. So just this sort of terminology, if you get it in there from the beginning, start using these words, then it won't seem so weird for students when they're used all the time at A-level, for those going on to A-level. So we do, because we often talk about solution, so that's the solution, but actually a solution to an equation is made up of all the roots. So the solution, so when it says solve this, if you only put one of these answers, you won't have solved it. You'll have only provided one of the roots. In order to solve the equation, the solution is both the roots. Okay, so that's just you know, pickiness, but pedantry is rife in maths, obviously. So, just some terminology. Now, for those that find it quite tedious to run through all the trial and error, there is a process called split, factorise, collect, which I had no idea about until I started teaching, and actually one of the students showed it to me. Particularly useful when you have a number at the front. So in order to factorise 2x squared plus 3x minus 5, what they do is they know that in order to get their brackets, they still need two things that add together to get 3. But instead of looking for two things that multiply to get minus 5, because we've got this 2 here, we actually want two things that multiply to get those two things combined, 2 times minus 5, so we want minus 10. So again, looking for two numbers that give minus 10 and 3, that bit's still the same actually. There's sort of a little bit of trial and error, that we need 5 and minus 2. The difference comes next, really. What they then do then is split this middle term into those two bits. So you can split it so the 3x is the same as putting in a 5x minus 2x, because that's how we got the 3. Once they've done that, they then take out a common factor from each of these two bits. So they consider this bit, the common factor, sorry, excuse me. Common factor is x, so they take out the x, and they're left with 2x plus 5. And then they look at this one. The common factor here is minus 1, and I actually would write the 1 there. I think it makes it clearer that they've taken out minus 1 rather than just minus to get that. This then means that if you've got x times that minus 1 times that, you can take all of that into one bracket so that it is in fact, I would actually probably write it at the front as well because the way it's done, that you've factorised it now to be x minus 1, 2x plus 5. This is really useful if, when you've done expanding brackets, you've done as we were talking about, where we said if we're expanding something, so one of the ways of thinking about it is, as we were saying, that you do the x times everything and the 3 times everything, or vice versa, you do x plus 3 times x or whatever. But that's quite useful, because if you're saying, okay, I do the x times everything in that bracket, and I do the 3 times everything in that bracket, I've realised that I can't remember it. I think is this the distributive to, yeah, this is distributive law, hopefully. Yeah, this is distributive law. It's not associative, not associative. Sorry, should have looked up my names of all my, the laws, the associative, commutative, distributive. This is basically distributive, that if you've got each bit, you can split them off. And I think that understanding that is the same as that helps with this, because then they recognise, okay, well, if I've got each bit multiplied by the same bit in brackets, I can collect those bits into a bracket itself. So this is called the split, factorise, collect, because the splitting bit is identifying what you split that middle term into, which you then do. You then factorise each of those 2 bits, and then collect that bit back into a bracket. And so there, you factorise that. Now, for those of us that can run through the possibilities for factorising very quickly, the trial and error route, this seems cumbersome. But for those that takes a really long time, this kind of provides an extra step, a process that they can follow in order to get towards the factorising. Have you seen this before, this method?
I've not, and it's baffled me a little bit. Sorry.
Fair enough. Robert, have you seen this before?
Yeah, I have seen it, but I've never actually used it. I think it does look awkward, and I'm knowing what my year 10's like, I'm going to be quite horrified trying to get this across to them.
Well,
I'm going to have to practice it myself a few times.
You don't have to teach this at all. I just thought I'd show you, because it was something that I discovered when I started teaching, which I just didn't know. And I did find that it helped some of them, but you're right, it really confused others who could just do it fine, by looking. So I did sort of say to them, well, don't worry about doing this then. So I think it really does depend on your class. And if you're not confident with it, then it's probably safer not to, because it could just lead to further confusion.
It's like you said, I think we know how to do it ourselves. We just do it by sort of looking at it almost.
Yeah.
But it's getting it across to the kids that's going to be the snag.
Yes, and I think that was it. I think I've had I don't show this to everyone, it just totally depends on the class. Some classes, they don't really know what you're doing. It's like you're doing magic in your head when you factorise. And for those ones, I show them this process. Because it's mainly for the ones where there's this number in front, where they just can't seem to fathom the possibilities, especially when it gets to being sort of 4s and stuff. There are various options. But anyway, it's just something to bear in mind when doing factorising. So this is the other thing that they fall into. When there's a number at the front, so 2x plus 5 equals 0, a lot of them just put that the answer is -5, because what they think that we're doing is just taking this number at the end and changing the sign. They haven't fundamentally appreciated that you are solving this little equation or thinking about what number you would need to multiply that by. So obviously if you did 2 times -5, well, you're just going to get -10 plus 5 is double equals 0. So yes, be aware that that's one of the misconceptions that the kids have. They watch you doing just a simple one like x minus 1 equals 0, so x equals 1. They think that all you're doing is just turning that sign around. They don't realise that you're solving that equation. So just make sure that's clear. Right, so I think this is for you to have a go. Yes. So have a go at factorising that one. I'm just thinking if I focus it. Yes, there we go. Good. Have a go at doing these two yourselves. So factorising them and solving the equation, however you like. Good. Just a reflection doing those. I think ultimately what it boils down to, again, as we said before, is just the fact that if they don't know their times tables, they can't run through it really quickly in their heads, can they? They're going 24, or and they're like 6 4s, and then they they get a bit stuck. If they even get that. So that you get a lot of them that just sort of write down 1 2 3 4 and go 1 24 2 12 3 8 if they're lucky 4. So they go down through it. It takes them absolutely ages. And then I think the other point to make is that they don't like writing things down if they don't think it's going to be 100% correct first time, do they? It's a real issue at the moment. And really doesn't work with maths because you need to be able to scribble it down and then be like, no, that's not right, try again, try again. The fact that I happen to just factorise the second one first time is complete fluke. I just thought, I'll start with 2x's and 2x's. Oh, great, that worked. But it could have been that I'd have to cross it out and try 4x and x. So I think it really, it's getting them to the point where they're happy to just write down lots of things, and that's great, but trying is great. So Robert, what did you get for the first one?
Sorry, trying to speak while the mic's turned off.
Oh,
I've got down to x plus 2 and x plus 12, so x equals minus 2 or minus 12.
good, excellent. Wayne, have you done the second one?
Yeah, I was trying to do it with the times in by 5 at the end.
Oh, right, yeah.
By splitting them up. But then I kind of just went back to doing it in my head almost. But I'm not sure if I've done it right. Came to 2x plus 1 and then 2x minus 5, but I haven't timed that out. So
2x, I think they should both be minus. 2x minus 1 and 2x minus 5. Because you've got the plus sign at the end.
Okay.
You know they're going to have the same sign, minus times minus.
Okay, so x is a half or x is 5 over 2.
Yeah.
Yeah, but I think I kind of confused myself a bit because I was trying to do it the method that we were looking at before.
Yeah, so to do it that other way, so we need 2 things that multiply to give 20 and 2 things that add to give minus 12. So as I just run through this, I first 4 times 5, obviously not going to make 12. 1 times 20 is not going to make 12. So I'm left with 10 and 2, and that makes 12. So 10 and 2, and because I've got a minus, it's going to be minus 10 and minus 2. So I can split that bit in the middle, the 12x, into minus 10 and minus 2. And then I look at this first bit here. Common factor is 2 and x, and inside I'm left with 2x minus 5. Now because of that, I know my other bracket has also got to be 2x minus 5, and in order to get that I need to take out minus 1 out of this bit. And then those 2 bits, so that bit and that bit, make my first bracket, so 2x minus 1, and those are both multiplied by 2x minus 1. So, yeah, it's a tricky one, isn't it? Because really you could just be like, well, if you've guessed, so if you...
I just need a bit of practice.
Yeah, I think what it's doing is it's avoiding them having to guess and try out, like, whether they have to have a 4 and a 1, basically, or whether they have to have a 2 and a 2. It just involves them not having to figure out which one it is, because it falls out and tells them. I think that's ultimately what it's about. So yeah, I mean, this is a process which takes out some of the thought processes, which isn't always good, but amazingly necessary. But anyway, yes. So that's factorizing. Now, quadratic. What does a graph look like for a quadratic function?
A U.
Mm-hmm. Yeah.
Or
An N.
parabola.
Yeah. Sorry, what did you say, Robert?
I just said, or the upside down version is, it looks like an N, either a U or an N.
You're an N. Which is called a parabola, the shape. Don't be afraid to tell them that from the start. U and N graphs. Maximum of 2x intercepts. It might not cross at all. It might touch, or it might cross, but it's only going to cross twice. And those are the roots of the equation that we just found. So, if you want to sketch this graph of x squared plus 4x minus 12, quickly factorising that x plus 2 and x plus 6 and x minus 2. So our roots are x equals minus 6 and x equals 2. So the roots of the equation are the x-intercepts, which means basically where the y value is 0. So here is the graph where it crosses at minus 6 and 2. The x squared is positive, so we know it's going to be a U shape. And in fact, when x is 0, so on the y-axis, we're just left with the value of minus 12, so that is our y-intercept. So just from being able to factorise and knowing a bit about it, we can draw and sketch the graph, which is something that they are required to do. There you go. I'm sort of making all the points like this. So, based on that, can you now sketch all of these 3 graphs? So factorise and then sketch it showing the x-intercepts and the y-intercept. Any of these are nice starters, you know, once they know a bit about quadratics. You can either sort of show them these sort of things and see if they can, you know, sort of factorising, if you show them those and ask them to sketch it, can they connect those two together and get them sort of getting used to it rapidly as well. So Robert, what does your first one look like?
First one, I've got the y-intercept at -60, and it is a traditional U-shape crossing the x-axis at -6 and 10.
Yeah. Oops. Wayne, what about the second one?
Okay. I got the first one fine, and then the second one I've got the roots as x is 3 and x is 2.
Yeah.
That's
fine.
And then the y-intercept would be 6, but that doesn't compute in my head when I turn it into a graph, because it doesn't go through the...
Because
it goes...
the y-intercept doesn't have to be between the two roots, okay? It could be to the left of it. You see? Is that the problem you were having? That it should be like this one. It doesn't look like...
Yeah, I was trying to draw the graph, and it was like, well, why isn't it in between it? Right, okay, yeah.
So that's the key thing. It doesn't have to be. I did exactly the same, because I went from doing this one, this is deliberate as well. You know, you do this one, then you're like, wait, hang on, that doesn't work. Have I got one of them wrong? Should one of them be negative, one of them positive? No, it's just saying, okay, it goes through up there. It doesn't have to, you know, the y-intercept is wherever it happens to be on the graph. It doesn't have to be between them. And Robert, what's happening with the last one?
Right, that last one just has the one root. It sits on the x-axis at the point 4 there, and obviously it's at the y-axis at 16.
Yeah. So some people think about it as cutting the x-axis at 4 twice, so it's kind of cuts and comes through, which is a bit misleading really. It is just sitting, touching the axis at 4. It's got a repeated root is what we're saying. So yeah, repeated root, and there it is going to be 16. Good. Okay, so is that okay? So if you
that's fine, thanks. Yeah,
if you've got a repeated bracket, then it's a repeated root basically, and therefore just sits there. So this is going the other way. So we've been factorising sketch graphs by saying, okay, if x minus 3 is a factor, then x equals 3 is that x-intercept, that's the root. What that means is if you are given a graph and you can see that x equals 5 is one of the intercepts, you know that x minus 5 is a factor. So you could take both the x-intercepts, make them into factors, and then you found your quadratic function associated with the graph. Particularly useful if you are modelling. So you come up with some data, or you collect some data, you plot it, it looks like it might follow a quadratic, so you decide where your axis is and you choose those 2 points, and they are your factors, and so you can find a quadratic that fits them. So the only thing to be aware of is that just because they have the same x-intercepts, they might have very different y-intercepts and be basically a stretch of the other one. So these two graphs both cut at -5 and 2, but as you can see, one is a lot shallower than the other. And so this one goes through at -10, but that one cuts at -30. So these both still have the same bracket, they are the same factors, but this one just happens to have a constant multiplied by it. And that's basically stretching the original graph. So here's the original two factors just as they are. And if you multiply by 3, it stretches them. So for any two factors that you find, you can actually have infinitely many parabolas through those points of some version with a k in front. This wouldn't be expected at GCSE or necessarily A-level, really. Perhaps C3 they would be looking for that stuff, but in A-level, but not really. Ultimately, they just want them to understand that if you're given a graph, you can find the equation for that graph. So, looking at this one, cuts at -1 and 5. So my factors will be x plus 1, x minus 5. So the equation of the curve is basically those two multiplied together and then multiplied by some constant k. So we can just write it in the generic k. Because at this point we don't know what that is. Now here, in fact, you are given the y-intercept, which means that you can actually find the whole equation. So this cuts at -4 and 2. So we know our factors are +4 and -2. I didn't realise when I clicked it, give you the whole thing. But the difference is that we're expecting it to cross a -8. So if we multiply out the two brackets, then we have actually got the correct curve because we want the -8. If you'd found that that was cutting at -16, then you would have known that actually this was going to be 2 lots of this graph in order to get that. So if you are given the full graph with the y-intercept, then you can then find the full equation for the curve. If you've only got the x-intercepts, it will be a family of curves. So using that, suggest equations for these graphs. So some of them you can see very clearly, and others, well actually I think there's only one that you can't tell. The others you can. So taking what you know about the x-intercepts and the y-intercept, write down the equations of the curves. I'm just going to go get some water because I'm losing my voice a bit. Robert, it's your hand up because you've done all of those. Right, Wayne. Do you want to start off with the first one?
Yeah. X minus 4, x plus 3.
Yep, good. Robert, the second one?
X plus 3, x plus 5.
Good, yeah.
We're going across the top.
Yeah, sorry.
Yep.
Yeah, so I work, yeah, put along the book. Wayne, the third one.
In brackets, I've got x minus 2 and x plus 3, and then a 2 on the outside.
Yeah, excellent. Yeah, good. Robert, the next one, so the bottom left border.
X minus 1, x minus 4.
Yes.
And the k is equal to 1 on that one.
Is it? Could you,
Oh,
do you
no,
know?
sorry, we don't know. Sorry, we don't know what that is because
Yeah.
there's no actual point on there. Sorry, I'm looking at the wrong one. Yeah.
All right, yep. Okay, so K is K.
Unknown, yeah.
Yeah. Wayne, the next one.
Looks like x minus 3 squared.
Yeah, good. Yeah, x minus 3 all squared. And finally, Robert, the last one.
I've got x plus 1 and x minus 7, but k is equal to minus 1 on that, which
Yeah.
will give an overall minus x squared plus 6x plus 7.
Yeah, absolutely. And hopefully the students would realise not only from the fact that when they multiplied it out that they had a minus 7, this is not cutting a minus 7, but also from the fact that it's upside down, it's an N-shaped, not a U-shaped. Good. So yeah, I always do my teaching of quadratics very much like I've been doing with you, where it's very much integrated, going back and forth between algebra and graphs, rather than being a really dry, standalone, just algebraic process. So we've been doing factorising, which has really helped us to find x-intercepts, but the vertex, so that's the max or the min point of the graph, to find that is why completing the square is useful, because it is related to translating the quadratic graph. So we're going to have a little diversion now into translations. There is so much involved within the topic of quadratics. It covers so many different little bits of other things. And so the students might have done translation somewhere else, or you can kind of wrap it all up inside and do it kind of all within quadratics at the same time. So that's what I'm going to do. So we've talked about the graph of x squared. This is the basic y equals x squared. For every value, it is just squared. So 1, 1, 2, 4, and so on. And it goes through 0, 0. Now, that point 0, 0 is the bit that's called the vertex. And here, it's 0, 0. And actually, I know that from looking at this graph because there's no extra bits. It's kind of plus 0. Which we'll talk about in a minute. Now, if I add a constant to x squared, so it's simply x squared plus 3, that's saying, okay, these are my y coordinates, x squared. If I add 3 to each of them, I add 3 to all the y coordinates. And therefore, it moves all of them up by 3. So where my y coordinate here for 1 was 1, if I add 3 to it, it will now be 4. And this one, 4, will now be 7. And so all it does is simply moves the graph up by 3. Now, as you can see, that's moved the vertex up by 3 as well. So the x coordinate hasn't changed, but the y coordinate has. So adding a constant to the whole thing just changes the y coordinates. I added 3 to it. If I add 3 to the x itself, so I add it to the x, then we square it because that's what we're doing for this function. what actually happens is, this is my original graph here, x squared. This is my graph of y equals x plus 3 all squared. It's moved the graph to the left by 3. It seems counterintuitive because we see a plus and we think positive. And that was true when we had just adding a constant to the whole thing. That was adding 3 to all of the y values. But now what's happening is we are saying what value has to go in here to make, for example, to make it 0, we would need minus 3. And so it ends up being the opposite to what we think. In order to add 3 to all the x values, what we're actually doing is to get the same result. So if you think about here, x squared equals 0. In order for the y to still be 0, when we've got x plus 3 squared, I would need the x coordinate to be minus 3. In order to get my same value of 1 as my y value here, when x was 1, for this to equal 1 and to solve it, I would need to have that, that equals 1. So that would mean that x plus 3 is the square root of 1, which is plus or minus 1. So we know that we've got two answers because it's quadratic. So either x plus 3 equals 1 or x plus 3 equals minus 1. When I solve those, I get x equals minus 2 and x equals minus 4. So although it might seem counterintuitive that when we add 3 to x, it moves it to the left, it's again because of this nature of the fact that we are solving this little equation when it equals the y value. It's the same reason why, the sign changes between the factor and the root. Ultimately, I sort of give this explanation, then I say to the kids, okay, when it's y values you're adding to, it does what it sounds like. So if you add things, it moves in the positive direction. If you take away things, it moves in the negative direction. It's the opposite to what you think when you've got x. So you add to the value of x, you're moving the graph to the left, to the negative way. And then ultimately, I think that's just what they remember. Adding, moving to the left, taking away, moves to the right. So here we go, we're just doing the same thing. If we do both at the same time, for example, here we are taking 5 from each of the x values and adding 3 to the y values. It can do both. So this will move it, so it's negative, it will move it to the right by 5, and then this one will move it up 3. So there is my new graph. Notice that my vertex here is 0, 0. My vertex here is 5, 3. And that is in fact the translation that has happened. It's moved it along 5 and up 3. So that's a translation written in vector form. And effectively that gives us the coordinates of our vertex. So when we write it in this form like this, which is how we were doing it here, we've got something in brackets with a square and then something on the outside. So x plus p squared plus q, that's translated the graph of y equals x squared by minus p, I mean basically whatever the opposite sign of that is, and then by q. And so the vertex is now minus p, q. You might sometimes see this written that that's a minus there in order to make that a positive there. It doesn't matter. All that you have to be aware of is that it's the opposite sign. The kids get a bit confused because they learn it by rote and then don't really appreciate that it's the opposite sign. So if that's negative, that will be positive. The vertex given by that translation, minus PQ, because what we are basically doing when we move the graph around is you can think of picking it up at the vertex and moving the translation. It's a helpful way to do it. And we'll talk about how to get this algebraically in a minute, but we'll look at sketching the translations first. Has what I've just said made sense? Wade, is it all right? Have you seen this before?
I've never seen it written down as a translation vertex, but yeah, it makes sense.
It's often not connected in this way, I think, graphically. And we'll get there basically algebraically in a minute by completing the square. Wayne, have you seen this before? Oh, you're muted. No. Can you hear me? Wayne, are you talking or you're not? Can't tell if okay. Well, I'll move on. Have a go then, if that makes sense, hopefully. Have a go at drawing or sketching the new graphs basically here. So
can anyone hear me?
Yes, I can now, yes. Were you talking before?
Okay, I don't know what.
I couldn't hear you before.
Yeah, I was talking. I don't know what happened there. Yeah, but yeah, no, I have not seen it, but it makes sense. So
good. Okay.
We'll see.
So have a go then at doing these, drawing the sketches of the new graphs. I'm not bothered about the y-intercepts and where those go. You can work them out if you really want to multiply them out, but I'm not bothered. I didn't just multiply them out, so I just put them in. Right, Wayne, you want to talk us through what you've done for the first one?
Yeah, sure. If you can hear me, just give me a nod.
I can hear you. Yeah.
Yep. Okay. Okay. Yeah, basically I've got it as a translation of -2 and then -1. So it's moved to the left.
Yeah.
by 2.
Yeah.
And then down by 1.
Yes, I actually looked at the graph. Yes, I have. Good. Excellent. Robert, what about the next one?
Yeah, I've got that one. The new vertex is going to be at 0.32. So that's moved to the right a bit and up a bit.
Good. Yeah. The last one is moved to the right by 4 and down by 3. The new vertex is 4. Good. So the reason for slotting translations in here, which is something that we've whipped through very quickly and would normally be like a whole lesson of just getting them to translate things around the place, is because it then gives some sort of understanding of why we do completing a square, which otherwise can be very dry and obviously just did not ever stick in my head. Oh, okay, so here it is written to go the other way. So quickly, to go the other way, can you write down the equations of those? So sketch them and write down their equations. Right, Wayne, what did you get as the equation for the first one?
X minus 2 squared minus 3.
Yeah, good. I wrote that down and then I did my sketch, whereupon I then translated it the wrong way. Whereas it's definitely easier if you pull the sketch first and then look at the sketch. So I don't get confused.
So it's gone right and down a bit, basically.
Yeah, good.
Yeah. Okay.
And Robert, what did you get as the equation for the other one?
Yeah, x plus 1 all squared plus 2.
Good.
So that's gone left a bit and up a bit.
Yeah, exactly. Good, so that is the relationship between translating and this new form of writing the equation, which is the completed square form. And as you can see, it is particularly useful because it tells us right away, if we're given it in that form, it tells us right away what the vertex is. To get to that form, when we're just given it like this, I do not know how they came up with it, but it is just this little funny way of doing it, where you look at the second term and you halve that term so that it's 7x. But really we just want to think about the numbers. So what I do is I'm going to write this myself actually. So I look at this bit, just that bit there, and what I do is I imagine that I've got one bracket, and I halve this to say, okay, that is going to be half of that is going to be the value at the end of my bracket, because if I add both bits, the 7x plus the 7x gives me the 14x. So I imagine that this is my bracket that I've got, because if I multiply that out, I get x squared plus 14x plus 49. So that is the same as my first bit here, except that I've got this extra 49 that I don't need. That's fine, because what I do is if I take off the 49, then that bit there is now exactly the same as my x squared plus 14x. Do you see that? Because having multiplied it out and taken off the 49, I'm left with the bit that I wanted in the first place. So I was just trying to find a way of writing that in a different form, which I've done. So you halve this number here and bung it in the brackets with the x. As you can see, well, I'll say this because the most common error the students make is they put an x in there too. And then when they multiply out, obviously, they've got extra x's, which doesn't make sense. The reason that it's just the number is because when we do the multiplying out of the brackets, we get back to our x squared plus 14x. If it's got an x there, it doesn't work. And if there's an x squared there, it doesn't work. So they get a bit confused about what they're supposed to be putting in brackets. But ultimately, it should just be a binomial term, like we had before when we were expanding brackets. Now, that's my first bit. I have also got this bit here that was already part of the equation. So, if I bring those two bits together, I'll erase this bit because that is exactly what's written there. If I, do the arithmetic, I've got the x plus 7 squared minus 25 equals 0. That is exactly the same as my original thing. And now I can see that the vertex is going to be minus 7 minus 25. You can also use this to solve the quadratic by just solving it. So you take that over, you square root it, so it's plus or minus 5, and then you add, so it takes 7 from each of those. It's not very commonly used. I do remember at school we used to be asked to complete the square in order to solve the equation. But generally, in GCSE and AS level, they don't specify how the students have to solve the equation. So we generally recommend that you factorise it or use the formula before you use completing the square because it is more complex. However, if you have already completed the square, I suppose it doesn't really make any difference. You may as well continue on to solve it that way. Okay, did you manage to follow that process?
Yeah, I'm happy with that, Sarah, thanks.
Have you done this before, Robert, the completing the square?
I have done. Haven't yet taught it with it. I'm not sure if it's in the syllabus for us.
Well,
but I have actually been refreshing my memory just in case actually it comes up.
Yeah, I have to say I don't think I've actually ever seen it taught at GCSE, even though it is on the curriculum. Whether it's actually in the syllabus. So what I showed you was actually the national curriculum. Whether it's actually made it into the syllabus of any of the GCSEs is another question, really.
Yeah, I think that if it is in there, they'll probably teach it to our top set, but the rest may well, they won't bother. Depends how they get on with the rest of the stuff. Yeah.
Ultimately, it's one of those things where it doesn't seem particularly difficult, does it? But it's just another step too far for some people. How was that straightforward, Wayne? Have you seen that before?
No, I've not seen that. Well, not that I can recollect, but yeah, no, I quite like that. I think the only kind of thing in my head, I'm guessing it doesn't work, but say it was 2x squared plus 14x plus 24.
Yeah. I will show you.
I guess it does.
Yeah.
Oh, right, okay.
Yeah.
Okay.
Let me show you.
I actually think it's almost simpler than, but maybe I'm being a bit hasty.
No. Do you know, when I went back and looked at my A-level notes when I was at school, we did this first. This was how I was actually taught to solve equations when I went through it, and I was like, really? So bizarrely, yeah. I think because this sort of process of taking things to the side and solving was what we were more used to. Anyway.
Yeah, no, it does. On that example, it seems very simple to
Yeah,
to
yeah,
do. I mean, you've really only got to remember you've just got half the 14, half that number,
yeah,
and the rest of it just flows.
yeah.
But yeah,
And this is why it's always a shame when we take things that we think are more complex and don't teach them to students, when actually it could be something accessible to them. But yeah, we don't really. I think it's because it's always been quite dry, so it, you know, if you have kids who are not process oriented and who, you know, are more visual and that sort of thing, they find this really tricky, which is why I always teach it with the translations. But if you've got one like this, we're just going to consider this first bit, and we're going to simply take out the 4 from the first 2 bits. You can take it out of the whole thing, but then you're just going to be left with a really horrible bit at the end. You know, it's like 5 quarters, and there's no need. We can just ignore that bit for now. Now we complete the square on this bit. It's still not fantastic because I'll do some square brackets and do it in here. So we still have to halve this 3. So it's going to be 3 over 2 or 1.5. That's still just the same process. And we're going to have to take off. So before I did this all and I multiplied it out, and you can encourage the students to do that, but ultimately all you're ever going to get is this bit, obviously squared, is the bit that you have to take off. Getting them to do it and multiply out every time can be useful because they get confused by the fact that when it's positive or when it's negative makes no difference. You're still going to be taking it away because it is the extra bit that you don't want. So some of them end up getting confused. They think they have to take it away in some situations, add it on in the other. But of course they don't, because whenever you square anything, it's going to be positive. So if we multiply this out, we're going to get x squared minus, what we're going to do, we're going to have 3 over 2x minus 3 over 2x. So minus, well, 6 over 2x, I'll leave it like that rather than making it bigger. So we get minus 6 over 2x, which is the minus 3 that we wanted. And we get plus 9 over 4. That's what happens if I multiply this out. So that bit is the extra bit I don't want. So I'll take away 9 over 4. And that's that bit. Meanwhile, I'll bring this down. I've still got plus 5. At this point, I then multiply the 4 back in. So I've got 4 times x minus 3 over 2 squared minus 9 plus 5. 0. So I've got 4 x minus 32 squared minus 4. Oops. Which actually works out quite nicely because when I solve this, I take the 4 over, divide by 4, it just equals 1 with square roots. So x equals plus or minus 1. And then in fact, if I delete all of this, I can just show you the action. Now they did it differently to me. Do you see? They took it out of all of it. And I just don't see the point because then you're left with this, which is fine. So when you then multiply it back in afterwards, it still gets you back to the 1. But I just prefer to just take it out the front bit and not have to worry about extra bits. So they haven't gone through something of that, but simply becomes 2.5 or 1/2. So those are your x values. In terms of your vertex, we're still looking at, actually, I'm just going to correctly. time to draw the graph just to show you. So 4 x minus 1.5. So the vertex, so there's the graph. Really excited to hold it up. I've just asked it to find the vertex. I don't know why it's freaking out on the 1.5 from the load of field stuff. But that's the graph there, and as you can see, it's moved it, as we would expect, the right by 1.5 and down by 4. So the 4 that's at the beginning doesn't affect the vertex, because all the 4 is doing is stretching the graph and sort of elongating it to make it a sort of tall, skinny graph. It's not having any impact on the vertex itself. So you still only have to worry about what's happening inside the bracket and then the bit at the end. Right. Have a go at completing the square on these. Is it 10 to 11? Yeah, so see how you get on with those, then that will lead us up to our break. We'll see what time to discuss them before the break. Wait, is your hand up? You've done all 3 of those already?
No, I haven't.
That's right. I was going to say that was incredibly fast otherwise.
Guys, I'm faffing around with this, so if you do want to crack on, Sarah, that's fine. I've had a go at number 1 and I've started 2, but I think I'm going wrong somewhere.
Okay, so what did you do with number 1?
So I did x minus 4 all squared,
Yeah,
and then minus 16
yeah,
minus 2
yeah.
is equal to 0.
Mhm.
So it's x minus 4 squared minus 18
That's fine.
is equal to 0.
Yeah, in fact, because it doesn't equal 0, actually, you don't actually have to continue to solve it. Sorry, but if I've given you ones that may not solve, I've just given you ones to complete the square on. So you can stop there. That's it. X minus 4
Right.
squared minus 18.
Right, okay. Right, that's why I'm probably struggling on the second one.
Oh
then.
yeah, the second one won't solve because you'll get a minus,
Yeah,
and you can't square root it.
that's what I've got.
Yeah.
I've got a minus number and I'm thinking to myself, oh, what am I doing?
Yeah, because what did you get when you completed the square on it? What did you get?
Which one?
The second one, what did you get?
The first one.
On the second one, yeah, the
Yeah, x minus 1.5 squared plus 0.75.
yeah, that's it. That's all I was expecting you to do. Sorry, I should have said. That's
Okay.
it. Yeah,
All right.
so just the last one to do, and then we'll just break off that. Okay, Robert, do you want to tell us what you got for that last one?
Right, I've got 2 brackets x minus 4 all squared minus 31.
Oh, I have got 2 brackets x minus 2 all squared minus 7. Because what I should probably have made clear is you can only...
I've seen what I've done. I've taken the 2 out and left the 8x inside. I haven't gone down to 4x.
Yeah.
So yeah,
I was
see
going to
what
say...
I've done. So that's going to be x minus 2.
Yeah, and then that will sort
Yeah.
itself out. The kids, though, what I should say, they forget about that totally, and they just halve it so that they then put in brackets 2x minus 4, for example. But the point is that I should have made is you can only complete the square when it is in the form that has an x with no constant at the beginning. So that's why we have to take that number out. I just remember that.
Say that again. Sarah, say that last sentence again, sorry.
So you can only complete the square on something that's got no number at the front here, like an x squared, plain x squared, or 1x squared, really. So that's why I took this out and then only completed the square on the bits left inside. Because what you could do, some of the students, what they'll do is they'll be like, oh, okay, so 2x minus 4 squared minus 6c, they'll be like doing that, just ignoring that. So just to make clear,
okay.
you can't do that.
So I've just done it again. Actually, I've got 2x minus 2 all squared minus 7.
That is correct. Okay.
Yeah.
So I will leave that. I'll just do this here. I'll leave it up on the screen so Wayne, you can work towards it if you haven't got there yet. They've done it by taking everything out, which I don't do. But we'll take a break now to allow for the 2-minute silence and be back at 10 past. All right. Would you need that long or?
Yeah.
Yeah. Cool. Okay. We're back at 10 past. Okay. See you then.
Bye.
So say when you're back, or put your hand up or something.
Yeah, back here, Sarah.
Okay. So the completing a square that we've just looked at, the ones that have the numbers in front of would never be given a GCSE anyway, but might be given at AS level. But even so, it's quite unusual anyway. But using them to sketch the graphs isn't really, I don't think, I'm not going to go all the way back. Actually, I'll go all the way back. Let's just go back to the beginning. Identify and interpret roots, intercepts, turning points, deduce roots algebraically and turning points by completing the square. Solve quadratic by, oh, and sorry, does it have solve quadratics by completing square? Just wondering whether, no, it does, yeah, so it does want you to sketch them when you've done that. So it could be a GCSE used so that if you were given this graph, this function, you could factorize it and find the x-intercepts, or you could complete the square on it first and then continue on to solve it, whichever is easier. So if we complete the square on this, we'll get x minus 2 squared plus 5. So sketching the graph of that, we know that that is going to have moved along by 2 and up 5. So to the right by 2 and up 5. So we can draw in our vertex there. So in fact, there wouldn't have been any point in factorising it, as we wouldn't have had any factors. And we can see that it crosses at 9 because we know that from here. And in fact, as you discovered on that second one, if it's plus here, so if it's adding on something at the end, it's not going to cross the x-axis. You're not going to have any intercepts because when you take that across, it becomes negative and you can't square root to negative. So it's quite a good indicator actually as to whether you can factorise it. But I wouldn't encourage the students to have to complete the square first just in order to discover that. But now that you know, if it's plus, you're not going to be able to solve it, so you're not going to have it crossing. So I have again uploaded various documents onto Student Central. And as I put here, I've said, you know, does your school, and I think I talked to you about this before, about whether they teach all the algebra and then link it to graphs, or do they do them together, and what do you think? Have we had this discussion before?
We recently did link it to graphs, but we took the entire equations, so y equals x squared plus 2x plus 3, for example, and then we broke it down between the points minus 4 and 4 and created a function grid, and we used that to plot. That's all we've done so far.
Yes. And that is fairly common to find on a GCSE paper. It's just getting them to do a table of values and substitute in and plot, and then to know that it should be a smooth curve forming the parabola through those points. I think that is definitely sort of the starting point. That you know, they always tend to start with plotting, don't they? Because sketching is something the students really don't like doing. They find that they think it's being inaccurate to not show it all, whereas actually at AS level, they'll never plot them. They will always ask them to sketch them. So I think that's kind of the transition between GCSE and AS level, as to whether they can get away from showing all the points and just show the key issues, which are the intercepts, x and y, and the vertex.
The main problem we found them is they they're not used to doing something that has more than perhaps 2 steps in it. And factorising and then going into graphs and then sketching and plotting the routes is quite a complex manoeuvre for them, and they don't seem to have the resilience even at year 10. So they've got a massive shock coming in year 11 when we step it up again.
I think this is one of the reasons we don't teach completing the square, because it is, you're absolutely right. It's when there's too much to do, you know, sort of, it's hard enough just to get them to factorise. So to take that any further, it's all too much for them, isn't it?
Even if I've got the rules, I've got perhaps 5 rules, step-by-step scaffolding on a PowerPoint on the board, and I leave it there through the exercise, there's still, it's just too much trouble for them.
I know, and every single one that they try to do takes them an absolute age. They don't seem to be getting any sort of automation to it. And it's funny, isn't it? Because I suppose as maths teachers, it's tricky for us because there's obviously a reason that we lent towards maths, which is that we didn't struggle so much. So yes, it is very interesting to see, isn't it, when things that don't seem so difficult really take a long time. Yeah, it is. It's difficult to know, isn't it? Because in some ways you feel that you're bombarding them with information if you try to link the two. But once you link the two, then it's more accessible, especially to the ones who find algebra completely abstract. Perhaps it's better to start with the graphs completely and sort of say to them, well, how can we find, oh yes, in fact, this links me to something I'm going to show you at the ISW. I'm going to show you a video of the ISW of someone teaching factorising, actually, something similar. Anyway, so I won't go into this too much, but at the ISW I was going to do decision maths with you, but they have taken it completely off the A-level syllabus. So from next September it will no longer be taught, which is very sad because it's one of my favourite bits. So I didn't think that there was much point in showing it to you, and instead I thought we could spend the afternoon doing problem solving, so as sort of more generic, but I could include a bit of decision in there just to show you a bit. But anyway, we will hopefully talk a bit more about this, about showing students how to link things, or not having to show them, but getting them to do it themselves. This is quite a nice activity. It's page 13 to 15 of the quadratic functions document I've uploaded, and you print them all out, and it's just a massive matching task. So when you've taught them factorising, completing the square, and the relationship with the vertex, the x-intercepts, the y-intercepts, and the graph, they can then match all of those together. And the approach, the woman who wrote this, Susan Wall, her approach was rather than to use this as a summary exercise, she would use this as a starting point, not all of them maybe, and see what they can discover. So that the students try to match them and then figure out, by multiplying these out, they would get that. And then try and spot the relation, get them to see that they can spot the relationships the other way, and that sort of thing. Because in order to get greater depth of understanding, but again, those are things that we'll talk about in the problem solving session. Now, the only remaining way to solve the quadratic that we haven't talked about is the quadratic formula. This used to be given just like this at the front of the formula booklet. It's not anymore, so for GCSE they have to learn it, which I think is better, because the problem was they were not bothering to learn it, getting into the exam, looking at the formula page and not having a clue what they were supposed to do with it. Key problems, they forget the minus at the beginning, or they put the plus or minus there, and they basically these signs, they get really muddled with these signs. They also forget, or just never realise, that it's the whole thing over 2a, not just this bit. They often just put this bit over 2a. Now, a good way to get this really secure in their minds, but would be something that you'd only ever do with top set because of the abstract nature of it, is that actually if you start with this and get them to complete the square on it, they will get to this. And that, I put that was the last thing in the self-study task, you know, where I'd left it. I put 2 extra ones which we said we'd be doing later. So that's for you to have a go at in the self-study task. Now the bit underneath, I'll go back, this little bit here, underneath the square root is called the discriminant. So b squared minus 4ac. This does not come up at all in GCSE. But AS level, they'll use the word discriminant and expect the students to know that that is the bit under the square root. And it's quite useful to see the relationship between this discriminant and the graphs. So if you calculate the discriminant for each of these and sketch, I'll sketch the graphs, you work out the discriminant, I'll sketch the graphs so that it speeds things up a bit. Sorry, it's taking me a lot longer, I'm sure, than it is you, to work out the b squared minus 4ac. I'm just going out for the future, doing this. Right. What did you get for b squared minus 4ac for the first one? Robert?
That first one I've got 49.
Okay.
Which is positive.
Yeah, exactly. So discriminant is bigger than 0. Wayne, what did you get for the second one?
-4.
Yeah. So negative. And Robert, what did you get for the last one?
I've got 0 there.
Yeah. So what do you notice about the graphs and the discriminants? Robert?
If it's a negative, you're going to find you can actually you can't square root a negative number there, so
Exactly.
you're not going to have any roots. So it will be lying above the curve,
Exactly.
above the x-axis. Sorry.
Yeah.
Conversely, if it is a positive one, you are going to be able to have a square root, so you're going to have 2 real roots there.
Yeah.
And obviously, if it is 0, then it will be lying on the axis itself.
Yeah, because when that bit's 0, obviously you're not adding or taking away anything, so you just get this one solution, which is minus b over 2a. So yes, that is the relationship between the discriminant and the graph. So that can be really useful. So it took me absolutely ages to draw those graphs because I completed the square or factorized each of them to get that information. Whereas the discriminant can tell you right away whether there's any point. So there's no point to me factorizing that because I'm not going to be able to. And I can test that by finding the discriminant first. So yeah, there's a nice gapped handout which I've uploaded, which is called Quadratics Conclusions, which has got about the discriminant. But again, this is all AS level. And this is just a useful tip about whether quadratics will factorize. If you do b squared minus 4ac and you get a square number, it's a perfect square. So here b squared is going to be 1 minus 4 times 2 times minus 3 gives you 25. So your square, because it's a square number, it tells you the quadratic will factorize. Whereas if you had, oh, and that's just it factorize. Whereas if it doesn't, it won't. But that's, these are just little tips, which, when you've given students a load of them and they go, I can't do this one, and you try to do it and you're thinking, what? Well, probably it doesn't factorize. This is often the problem with making up quadratics. So always, as you would when you prepare a lesson, you'd have a list of ones that do. Yeah, if you want to test, you can do b squared minus 4ac in your own check. So this one, not a perfect square. So x squared plus 5x plus 3 doesn't factorize. I mean, it's fairly obvious, isn't it? We could check right away by saying, okay, I need 2 numbers that multiply to give 3, which would be 1 and 3. That doesn't make 5. So I know right away anyway that it won't factorize. And you'll have to use the formula. Don't fall into the trap that some of the students do, which is that they think that if it doesn't factorize, then they can't solve it, or that it doesn't have roots. They forget it just means that it doesn't have integer roots, it doesn't have whole number or nice round rational roots. It just means it is not necessarily a rational number. It could be some never-ending decimal or just generally a decimal. They're not going to find by factorizing. So they do get a bit confused about factorizing and solving, I think, perhaps. Just because you can't factorize it doesn't mean you can't solve it. So that was a starter that I had done, which I put in there and some bits and bobs. But I'm going to move on now because I have actually got quite a lot more to do now. Really helpful, I haven't started kinematic yet. Simultaneous equations. When you have 2 lines and try to solve simultaneous equations, we generally use either substitution, where you can make them equal, or we in general use elimination, which is where you multiply the top one by 2 and the bottom one by 3 so that you get something the same. With a quadratic, you have to use substitution, or effectively, if they're both equal to y, they're equal to each other, so you just make them equal to each other. And that's what's happening, because graphically, we are basically talking about where this line crosses the quadratic. That's what it means to solve simultaneous equations. It's saying at what points do they meet. And, oh, I'll skip over the problem. So in terms of how you can use the discriminant to help you, obviously, so just take it down completely. To solve these, if I make these equal to each other, because they're both equal y, that at that point that they'll share that y coordinate, they will also share their x coordinates, you can make them equal to each other. In order to then solve this, you have to collect it all on one side and make it equal to 0. So I'll get x squared minus 3x plus 2 when I collect that all on one side. I can then solve this as I would any other quadratic. Now, rather than bothering to do that, just to show you how many roots, we can now use the discriminant on this. So b squared minus 4ac is going to be 9 take away 4 times 2, so it's going to be 1. So it's going to be positive. Because it's positive, that would, for this, if I was drawing this graph of this function, would tell me that there are 2 roots. But because this is made up of these 2 functions, what that means is that it crosses twice. So I know that I'm looking for 2 solutions. So when you're solving simultaneous equations, if you get down to this quadratic here and the discriminant is less than 0, that means they don't cross. It would be weird, obviously, to be given 1 because then you couldn't actually solve it. If the discriminant equals 0, then one's a tangent, so it just touches it. And if it's greater than 0, then they cross. Bizarrely, I thought I had a slide about this, so we know this because I've just told you something that comes up later. Just quickly looking at inequalities, when we look at linear inequalities, they're fairly straightforward. All we have to remember is that if we divide by negative, we turn the sign around. If we want to solve this, we still have to think about what we know about quadratics, which is that we can only start to do things with them if they're equal to 0. So we actually rearrange it to get a 0 on one side. And then we're going to have to draw a sketch of this. So if we factorise it, we can sketch that curve. So this is the curve of x squared plus 2x minus 3. We want where it's less than 0. So that's basically saying where the y values are all 0, so that's below the x-axis. So we're saying, okay, what are the range of values that satisfy when this graph, x squared plus 2x minus 3, is below the x-axis? These are the range of values here, so where all this bit of the graph is the bit below the x-axis. So the range of values are between when x is minus 3 and x is 1. Because it doesn't include those, we're going to have x between minus 3 and 1 using just the less than signs without the less than or equal to. So because it's just one bit, this bit here, you have one inequality. Had we wanted greater than 0, it would have been the values of x at these points going on and these points. So there'd have been two inequalities. So had it been greater than 0, the range of values for x would have been when x is less than -3 and when x is greater than 1. Inequalities are things that students generally find difficult. They seem to find that these signs, they get very confused about them, and that one is very particularly less than, one is very particularly more than, that you can't turn them around, and they just generally don't get them. So if, I mean, this is technically GCSE, however, I mean, but I haven't seen the new papers anyway, but I can't imagine there being very much of this. This would be very much the top end stuff, which is why I haven't put too much in about it. It's very much AS. It will come up a lot in AS. And my AS students really struggle with it. So I'd leave that here for you to see, but going to move on. Another extension that comes in at AS level is that if you were given something that looks like a quadratic, but actually it's like a quartic here, you can say, okay, well actually let's say that x is t squared, then I can write it as a quadratic. Then you can solve it just the same as a quadratic, and then remember that x was in fact t squared, so then you can find what t is. It's just a little extension that they put in the AS level. And unless you've been shown it, coming up with it would be pretty amazing to figure it out. So this would be the same sort of thing. If you were given this, how could you solve this one? Well, again, I mean, that really is very difficult to tell that could ever look anything like a quadratic. But if we let root t be x squared and rearrange it, then we actually do get a quadratic that we can solve the other way. But you know, obviously this is AS, and this is the very last question that they would ask on the paper as an extra. Yes, this is in fact, by doing the root one, it's actually created two roots, but one of them is not actually possible. Anyway, so that was quadratics. I'm sorry that that last bit was very rushed, but it was just to sort of show you some other bits. But they really...
Sarah, just going back to that last one, could you just square both sides, which would get rid of the root, and then transpose them all around? So you'd end up with t, and then 6 minus t all squared, and then just work out that way.
That does feel like you'd want to do that, doesn't it? 36 minus 6. I'm having difficulty with that, but over 9 and 4. No, minus 13. Yeah. So 9 and 4. Yeah, it works just the same. Works just the same. Still, you end up with this, getting 9 and 4. And again, you've just got to be careful that actually that wouldn't have worked. If you put the 9 back in, 6 minus 9 is 3. Sorry, 6 minus 9 is minus 3. Root of 9 is 3. And minus 3. Well, 4 minus 3. No, that does seem absolutely fine, doesn't it? Yeah, no, that would work this time. Yes, so actually that would be typical, wouldn't it? Kinematics, I've tacked this on because just originally that's something that was new. I think it was stuff that was new or sort of had more advanced stuff in the new GCSE, and that's why I put them together. So very basic kinematics. The students come across, beginning of secondary school and quite used to, so speed, distance, time. This is just my little comparison about what used to be given. So the basic formula and the distance time graphs have always been at the lower end of GCSE, they're still there. But now there is the use of constant acceleration equations, which we call SUVAT equations. They were still in the syllabus for physics anyway, but they've just brought them across to maths to support the fact that they're already in physics. And I'm not completely sure yet what they look like in terms of the actual questions. I really need to get a copy of the last two GCSE. So distance, speed, time. Have you guys taught this at all yet at school?
No, not yet.
No, I've touched on little bits of it with the Year 8 class, but nothing formal.
Any ideas how you remember them or how you can help students to remember them?
I used, similar to the SOHCAHTOA and TRIG, the little triangle.
Yeah. Yeah, me too. And it's nice because it's in alphabetical order, sort of going round that way, which makes sense to me. Whether it makes sense to students, who knows. But it's particularly useful in this case with the units, because then they can realise that because this is a dividing line, this is a multiplier, so a distance would be kilometres over the hour, because distance is over time. What's the difference between speed and velocity?
Got direction, is it?
Yeah. Yeah. Good. Yeah, velocity is a vector, whereas speed is just a magnitude. Again, it's not something that they particularly, grasp tremendously at GCSE and below. But this is a typical grade D question. We're given a graph. I'll have a quick go at it anyway. Something nice and easy to do. So, okay, so you can't do the last part, obviously. You can't draw one on the screen, but well, I can draw on the screen. So, how far did John travel in the first 30 minutes?
5.
Yeah. What time did he start moving again? Yeah. He had a rest for 15 minutes.
9:45.
Started 9:45. How can you tell after that he was travelling more quickly?
He's got a steeper gradient on there. He's covered more distance in a similar amount of time.
Yeah, exactly. And then he's obviously stopped for lunch or something in Milford. And then he cycled home at an average speed of 20 miles per hour. They would just be expected to draw that on. So 20 miles per hour, well, he's 20 miles away. and it's an hour to get there. It's really nice, except the fact I don't have a ruler. Almost pulled off. That would not actually score me full marks because, of course, not a ruler and not actually gone to there, but anyway. So hopefully that would be fairly straightforward for most students. I think the main thing is you've just got to say to them, you've got to check what it is. Is it distance time graph or is it speed time graph? So what does this mean? What's going on? So this is another way to do that. I'll skip. So here's the distance time graph. Distance from Julie's home to the airport. Oh, so she drove from her home to the airport. So she's driven from her home to the airport. Must be 40 miles away. Pick someone up. Or waited there just generally, and then driven home. So how long did she wait? They can tell that that's the waiting time for that. How do they work out average speed? Journey home. Either of you, how do you work out Judy's average speed on her journey home?
You'd be working out the entire distance covered divided by the total time taken for that journey.
Yeah, as it's just.
I would take account of all the breaks. So yeah.
Because this one just says journey home from the airport. In this case, actually, you only don't need to do the 40 divided by the half hour. But you're right. For an average speed on a whole journey, you'd need to do that. So yeah, she travels at 80 kilometres an hour. Oh yeah, kilometres. That's probably that. So these are the sort of things that the students are used to. Now, all of a sudden, they have made what were really nice, simple questions into possibly things that will be beyond a lot of the students. So these are the constant acceleration formulae. They only apply when the acceleration is constant, not that students will be dealing with non-constant acceleration. But these three, this is basically how they're given the formulae. These now are given to them in the formula booklet or formula page at the front of their exam. So it does say to them that what each bit is. So A is the acceleration, U is initial velocity, V is final velocity, S is displacement. So this brings up a lot of words that obviously we don't normally bother with at GCSE. We've really only talked about speed, distance and time and acceleration, but we don't necessarily relate that to vectors and talk about velocity and displacement for vectors for speed and distance. So it's just another lot of vocabulary, formulae, which a lot of students absolutely hate. They really struggle just to substitute in formulae, unfortunately. And so not only do they have to do that, but they have to identify which ones they want. So a typical question, this is from additional maths. I need to look up now the papers. They should hopefully now be published for this summer to find out more about those. But the car moves from rest with constant acceleration on a straight road. When the car passes point A, it's travelling at 10 meters per second. When it passes point B, further along the road, it's travelling at 16. And it takes 10 seconds to travel between them. So you're asked to find the distance and the acceleration. So if I draw my little diagram just to help me, we want to find this distance, which I've put D, but actually is called S here. At this point, we do single arrows to show speed. So they've gone 10 there, and they've gone 16 there, and it's taken them, t is 10. So the key thing about the SAD equations, which is what they call the constant acceleration equations, is it's easiest if we write down what we know. So they're called SAD just to help you write down what they are. So S, the displacement, is what we want to know. The U is the initial velocity, so that was 10. The final velocity is 16. The acceleration we also want to know, and the time is 10. Now, if we look back to these formula that we've been given, this first one, B equals U plus AT, we've got B, U and T, and we want A. So that would be the one that we'd want to use for this one to find the constant acceleration. For this one, the displacement, both of them include finding the constant acceleration. So actually, it's a bit funny that it's asked us it that way round. You'd have thought they would have said find the acceleration and then find the distance because it'd be easier to use the acceleration. But it doesn't matter. I suppose there is also the fact that the distance is the change in speed, change in velocity. So like it always was, so it's the change in velocity over time. So you don't necessarily need to use the fancy equations here. So 16 minus 10 is 6 over the 10 is just 0.6 meters. So acceleration, oh no, what am I doing? That's rubbish. Should have stopped me. Talking absolute rubbish. Right. Change in velocity over time describes acceleration. So ignore what I just said. Acceleration is the change in velocity over time. Speed is the change in distance over time. So really that doesn't help us. I'm still inclined to work out the acceleration from this formula, which was in fact exactly the same, because if we rearrange this, we get our v minus u, so our change in velocity over time, which is what we just calculated, which was 0.6 meters per second. Meters per second per second. So we can write it like that, but we generally write it either as meters per second squared or meters per second to the -2. So those are all the ways we can write the units for acceleration. In the same way, you see that the velocity here is written as ms to -1. How much kinematics have you done before? Was this something that came up in your professional lives, Robert?
Not a great deal. I can still remember it back from O-level maths and physics. I actually, quite geeky-wise, I quite enjoyed this stuff.
Yeah, it is more typically, not to be so difficult, but it is more typically enjoyed by boys because it is more practical, and you know, they like to have kind of an idea of what is going on, and this is very clearly something's happening, you need to find an answer, and it makes sense. I hate it. I've hated it since physics.
Can you hear me?
Sorry?
Can you hear me, Sarah? Can you hear me?
I can now. Have you been talking before?
Yeah, I don't know what's wrong with my headphones.
Sorry, we can't.
That's all right. All I remember, this was all in physics.
Exactly.
It was never in maths when I did it. But,
yeah, it was all in physics. Yeah. So this is what's new. They have just moved this into maths now. So what I don't know, and this is what I was just thinking as I was doing this, is that I have no idea what they look like in the GCSE, but I haven't seen this summer's GCSE paper, which I should really get a copy of and see if they put it in. So this, and I think it's because this was all in physics, that they've now put it into maths, because the whole point is that maths is supposed to be supporting all its other subjects. So although it involves doubling up, hopefully there'll be that crossover where they'll be like, oh yes, I remember this, we've done this in physics. So, and I'm not sure how much depth they're supposed to go into, whether you just say to them, look, you've got these formulae, identify what information you've got, and then put it into the formula that you know you've got the bits for to find out what you want. And I think that really is going to be the case. So these two are two add maths questions. This is an M1 question, and it's really very similar. It's you know, got car passing. It's all about cars and things that, you know, vans move, things that move. And again, it asks for speed time graphs, and then to get them to calculate acceleration or deceleration in this case. So I wasn't going to say a great deal about this really. I've just kind of left these here because I don't know the nature of them at GCSE. All I'm doing really is alerting you to the fact that these are now in the exam. So where this was something quite nice and easy that the students just had to know really about distance time graphs, and they just had to know that the gradient was the speed, and then speed time graphs where the gradient was acceleration. Now they kind of need to know a bit more, but I'm going to show you actually.
what does M1 mean? Is that just mock, is it?
No, that's mechanics 1. So at AS level, or A level, the currently, and this is only for this remaining year, the A level is split into modules. So the AS is made up of C1 and C2, so those are core modules, plus one application, and that can be decision maths, mechanics, or statistics. So that was D1, S1, I can't remember what order I said it in, but M1 is mechanics, D1 is decision, S1 is statistics. At A level, you can then go on to do S1, D2, S2, D2, M2. So that's what the M1 stands for. It's just the first applied module for mechanics. However, from next September, they're introducing the new curriculum for A level, which there will not be modules. There will just be, they take all their exams at the end, like we did when we did it. And they have one paper that is pure maths, one paper that is pure maths, and they have one paper that is pure maths and there'll be some statistics in it, one paper that's pure maths and it'll have some mechanics in it, and one paper that is pure maths which will have some comprehension in it. They have no choice about modules. every single student will take those 3 papers, and those 3 papers will make up the A-level. So there is no decision maths. That's why I was sad they've got rid of that. And there will not be, in fact, as much applied maths. So there's going to be sort of more core overall. It is a return to what maths was like 20 years ago, what maths level was like 50 years ago, basically. But I mean, it used to be that there was pure and applied, so you could just do pure, and then you could say, oh no, I did pure and applied. But they put the applied in there as well. So this M1 will cease to exist, in fact. So yes, that's just a bit of a meandering into what the A-level is going to look like. It's going to be very different to teach, because what's always happened is we've sort of gone, okay, let's teach core 1, now let's teach core 2, now let's teach mechanics. So they'll be much more integrated throughout the year, going between them, because you can just teach things whenever you like, because they're not doing it until the very end. But what I was going to look up was the new GCSE curriculum. Yeah. Just to see what it says about kinematics and show you the kinematics, because for some bizarre reason I've not copied that slide across. I've just done sort of old versus new. But okay, fine. Oh, I really did it. What is it? I'm sorry, clearly I've upgraded my Adobe Acrobat and have absolutely no idea what's going on now. So, where is community algebra? Where is community? Okay. No, there is so, calculate or estimate gradients of graphs and areas under graphs, and interpret results in cases such as distance time graphs and velocity time graphs. So that means they're also expected to know that under a velocity time graph, the area gives you the distance. So I think maybe this is why I didn't copy it across, because actually they haven't put kinematics as a separate thing. It's just kind of integrated within bits of it. So it's somewhere around here, must be the C applications. Interestingly, I can't actually find where it talks about the kinematic equations. Plot and interpret graphs. Here we go. Find approximate solutions to problems such as simple kinematic problems involving distance, speed, and acceleration. So that's using graphs. And then that means it should be in here as well. That isn't so. Interpret the gradients to point in a curve. No, so interestingly, I've said this, but I can't actually find any evidence to suggest that it is in fact on here. High formula. What's that result? So it's one of those things that I thought was going to be in there. I can't actually see it. Oh no, I know why I thought it was going to be in there, because here's the formulae that they're going to expect to know. This is why. Yeah. It says the candidate should be able to use but need not memorise these formulae. This is what's going to be given on the formula sheet now. And because the kinematics formulae are there, it's kind of assumed that they'll need to know that. But in fact, they haven't given any indication in the syllabus that it's included. So I've kind of brought this to your attention, and I'm saying, and I actually have no idea at the moment, which is why I think I'd put these in here, to sort of say I have no idea what sort of questions they're going to be asking about them, or if they are. So all the traditional ones will still be there, but I will in fact look up some more about this, and we will do some mechanics next year. So we'll talk about this more anyway in the mechanics then. But sorry for that weird sort of foray into a bit of kinematics. Any questions generally?
No, fine. I've just been looking at my higher maths for the GCSE here at the kinematics, and the questions are not actually that dissimilar to that. Like a train starts from rest and accelerates at 3 meters per second for 15 seconds. What's its final velocity in kilometers per hour?
Yeah.
So they've got to use the formula and then put it into kilometers rather than meters per hour, or meters per second. So it doesn't look like it's anything too taxing, other than it's just a different branch they haven't been used to before.
And
it's not even physics. It's not even what we used to do in O-level physics.
No. There's no momentum. There's no things crashing into each other or anything yet. And the I think one of the difficulties is going to be this. It's worded like this. There's a lot of words, and it just looks a bit boring. So, just trying to get them to do it, and subbing into formulae, they find that really difficult. But anyway, my approach would be the same as I take it in M1 at A level, is basically get them to write Subat down their page and to write out what they've been given, and then they can identify which one they need. Because that's the difficulty, is like, what have I got? What do I need to put in? That's all that's going to take their time. And sort of an understanding about deceleration being negative acceleration, so just sort of words and everything again. But yes. So in terms of your which board are you doing? Robert, is that at Edexcel?
Yeah, we're doing Edexcel.
Yeah. So
we are as well.
Oh, okay. Well, that's good to know.
AQA.
Are you doing AQA?
I think it's AQA. I'm not sure, to be 100%. They're focusing on the Edexcel papers, but is that because they're the only ones out at the moment? Is it or something?
Well,
am I talking gobbledygook?
No, they should all. I'll just look it up now. Actually, they should all have papers. So what is this? AQA.
If they're all out, if they're all out, then we're doing the same one as Robert.
Oh, you're doing Edexcel.
That's what we're focusing on, all the papers at the moment. So.
Okay, let's look up Edexcel then. Edexcel was always sort of the more, I don't know, not thorough board. It's got a good reputation for being quite quickly. So someone's done a, it's always tricky. Without official logins, you can't get the papers, which is a bit annoying. Can't seem to now fresh on my computer. No, see there's the predicted papers, but no one's actually put the actual one that was from this year. So lots of people have now done the answers. Honestly, it seems like loads of people run out of their exams, do answers and post them, don't they? I wonder why they care. But anyway, so none of the official ones. If I go to Excel itself, actually that on this one. This is the results. Exam session, results will be released 20th of August, 31st of October. So it's only just happened. So that's why they haven't yet put up the qualification. So if we go to anyway, I'm wittering around. I will let you get on, but on these places you can find teachers. The thing is, it might make me have to log in. Let's see if we can find results. No, they won't. Yes. The wrong place. Hang on. Ed Excel. Jesus. Within the last 9 months can be accessed only by registered centres. Okay, so that's why. So that's why we haven't yet seen the summer one, and I still have no idea because I still can't see it for another 9 months. Yeah. So what goes through it went into who? Okay.
What paper have you got then, Robert?
Sorry, say that again, Wayne?
He's got
paper have you got?
You got the curriculum.
Yeah, we've actually got one specimen paper from next year's new curriculum. They pushed one out, and that's all we have at the moment, 2017.
Yeah.
I've just been trying to look for it there, but I do have it somewhere.
I don't like this new website. I can't find my way around at all. In fact, it seems to be having real problems with my, I don't know what it's doing, but I shouldn't be able to see the code, should I? Really weird. The website is obviously going a bit doolally today. Because normally it looks really quite straightforward. So, what is going on? Yeah, this has all gone a bit weird. I don't know why it looks so bad. Look, I'll show you what it looks like on another one. Because that is much easier. So this is what it normally looks like, and they put up all the papers, and you can go in and see them. But the 2016 doesn't go up until sort of February, March, April time next year. So that's why it's really annoying at the moment. I still can't tell you what it was like because I wasn't in the school. So when you're in school and there are exam papers lying around, as there will be right after the exam, nick one before your exam officers can get to them and take them all away, because then you'll know what. So here's the exams from June 2017. Oh yes, no, hang on, what year are we in? This is 2016, we still haven't had it, have we? Ah, sorry, that's why they don't exist yet, and we still don't know, because it's next year. Getting ahead of myself. So here's the spec, and here's specimen papers. Let's see if it's take away. It's much easier this time. So specimen question paper. Here's a higher specimen question paper. So some percentages, indices, conversion of units, straight line graphs, scatter diagram, some fractions, linear inequality, sequences, ratios, median, some area involving algebraic expressions to get a quadratic, some triangle stuff, some SOHCAHTOA, some probability, standard form, lots of angles, just generally working stuff out, volumes. Really? Okay, yeah, special angles, nice. We'll be doing that next time. That seems quite harsh. Is that the last one? No, not quite. Tree diagrams. Circle theorems. Surface areas. Vectors. Oh, there we go. Here's a velocity time graph. So here we go. We actually, yeah, we don't have. We've got a change in velocity. Work out the average acceleration during that. So we're going to need our, final velocity minus our first one over the time. Estimate the time during the 50 seconds when the instantaneous acceleration was equal to the average acceleration. So whatever they've just worked out, they're going to have to then draw lines on their graph to find the gradient for that. And they want to see that working. Okay, so that is still graph work. So that's all still graph work, but a bit more complex than previously done. Some algebra. Gosh, it seems like a terribly long paper, doesn't it? I wonder how long that took. How long that is. Yeah. Hour and 30 minutes. Wow, you've got to be working at quite a pace to get through all that, haven't you? No calculator. Well, I guess that's just part of the whole bit about it. And there seems to be 3 papers now. Another hour and a half. This one's a calculator paper. So you're more likely to have a SUVAT equation on calculator paper, I would imagine. Wow, that does not look like fun, is it? Here's a sketch of the graph 17 minus 15 cos x for one complete turn of the wheel. P is the highest point of the graph. Work out the coordinates of P. Wow, that is interesting. So look at this. This is trigonometry, which we will be looking at next time. Really harsh, I think, really harsh. Sorry, I've gone totally off and it's time to stop. There's a quadratic with a bit at the beginning. Using your answer to part A. Oh look, no, there you go. Completing the square can be written in this form. Work out A, B and C. So they are getting them to complete the square on one that's got a constant in the front. 3 marks that is for that bit. So there you go. As you can see, the particular square stuff that I showed you in fact is on there, and they're expected to know it with a constant at front. So even though it hasn't given us much information about kinematics, as I can see, it gives us a bit more information about that. Anyway, thanks very much for being able to change the 3rd of December one to 2 weeks' time. We will do trigonometry then. And I've already sent out, no, I haven't sent out an announcement for that, sorry, I will do the announcement for that probably next Wednesday. So I will talk to you in 2 weeks' time. You got any more questions or anything else you wanted to say? No? Okay.
That's fine, thanks, Sarah.
Okay. Do you guys want to talk to each other at all if I leave you on, or? Okay. It's up to you. I'll stop the recording.